Our review session for 8.1 to 8.3 quiz is taking place tomorrow. So jumping right in, we want to, again, please not forget, I suppose, you know what, I want to back up here. So we're focusing on this first little explanation. Please don't forget on the quiz that we're covering 8.1, 8.2, and 8.3. I know that, as we've talked about before in class, that we generally have a tendency, I suppose, human nature, to focus on the most recent stuff. So again, it's not like the entire quiz is just all inverse stuff, because that's what we did in section 8.3. We want to remember that quite a bit of what we're quizzing over, again, since we're covering all three sections, you will see some easy stuff on the quiz tomorrow as well. You might be of the opinion that all of this stuff is easy. I hope that's where you're at. But again, please understand all of the different types of problems that you've been exposed to through the notes, through the homework assignments, all of the different types, like I said, that we've been working on. And please expect to see, again, a nice blend of those problems on tomorrow's quiz. So, jumping back into this one, in number one, it just says to write the system as an augmented matrix. So if we're to write this as an augmented matrix, all that we need to do is basically change this from system to matrix form. So my first row is going to be 1, -3, -5, 1. My second row, because technically this is 0x, is going to be 0, 1, -2, 5. My third row, again, technically having 0x plus 0y, is going to be 0, 0, 1, -1. Since we're augmented, we're going to have that vertical line. So there's my augmented matrix. So the next question that we have here, again, look out for the easy ones. What is the order of the augmented matrix? So remember, it's always rows by columns, rows horizontal, columns vertical. So it looks like we have 3 rows by 4 columns. Going on again, it's asking us to perform the elementary row operations to this augmented matrix to get into reduced row echelon form. So we are currently in row echelon form right here. We want to get into reduced row echelon form, which means that we need to get zeros above the diagonal. Okay, that that being requested or that being asked now tells us at least where to start. So I'll try to copy that down here, but I still need to be able to see it. So if this is my initial, again, 1, -3, -5, 1, 0, 1, -2, 5, and 0, 0, 1, -1. This is my original matrix. We need to get to work. So typically we start in the top left in row 1, column 1. We work our way down the first column, up the second column, up the third column. So going with that same pattern, working down the first column, everything's all set. Working up the second column, everything's perfect until we get to the -3 in row 1, column 2. So that's the first adjustment that we plan to make. And that's occurring in row 1, which means before I do anything there, I want to reiterate the fact that rows 2 and 3 are staying exactly the same. So since I don't want to accidentally change anything there, that's what I'm going to begin with. So thinking about that -3, I have to turn this into a 0. The way that we're going to get there is to add 3 by using some combination of another row. So I believe if we take 3 times row 2 and then add that to row 1, that this should work. So looking at row 2, 3 times 0 is 0, plus 1 is 1. 3 times 1 is 3, plus -3 is 0. 3 times -2 is -6. Excuse me. Plus -5 is -11. 3 times 5 is 15, plus 1 is 16. So from here, we're getting closer. We're done with the first column, done with the second column. Moving over to the third column, working our way up. Row 3, column 3 is good, but row 2, column 3, we have a positive 2. We need to make an adjustment there. So now that we're looking at row 2, that tells us that row 1 stays the same, and row 3 stays the same. But row 2 is about to be adjusted. So again, I need to turn that -2 into a 0. The way we're going to get there is within that third column is to add a positive 2. So I think that we're to take 2 times row 3 plus row 2, that we should get there. So 2 times 0 is 0, plus 0 is still 0. 2 times 0 is 0, plus 1 is still 1. 2 times 1 is 2, plus negative 2 is 0. 2 times negative 1, negative 2, plus 5 is 3. Getting closer, last target that we have in order to be completely in reduced row echelon form is to look at our negative 11. And go. Looking at our negative 11, we need to figure out what to do next. So I need a 0 in that first row, third column. The way that we're going to get there is by adjusting row 1, which means that row 2 stays the same. 0, 1, 0, 3. Row 3 stays the same. 0, 0, 1, negative 1. Again, that first row is about to be adjusted. How do I turn a negative 11 into a 0? We have to add positive 11. So utilizing 11 times the third row plus the first row should get us to where we want to be. So 11 times 0, 0 plus 1 is still 1. 11 times 0, 0 plus 0 is still 0. 11 times 1 is 11, plus negative 11 is 0. 11 times negative 1 is negative 11, plus 16 is 5. So our job was to get into reduced row echelon form. We've done that. I just need to go back and look at the directions here. We put it in reduced row echelon form. Now it says to finish by writing the solution to the system. So remembering the solution to the system, we now know what this truly means. If I change this back to a system of equations, again, and I were to really legitimately do it this way, again, I'm trying to recopy my reduced row echelon form that we came up with. What this is truly saying, since we have our x, y, z columns along with our constant, this is telling us that 1x plus 0y plus 0z is equal to 5. 0x plus 1y plus 0z is equal to 3. 0x plus 0y plus 1z is equal to negative 1. Thinking about what all of this cleans up to get rid of all those 0 y's, x's, and z's, and whatnot, it's going to say that x is equal to 5, y is equal to 3, z is equal to negative 1. And the way that we would write this out, of course, is as an order triple, 5, 3, negative 1 for our final solution. On to the next problem then. It's kind of a combination here. It's asking in problems 2, 3, and 4 to use the following matrices to find the following if possible. So looking inside that red box, we have matrix A, B, and C. A is a 3 by 3 matrix, B is a 3 by 2, and C is a 3 by 2. So we're asked to find 2B plus 5C. So if I were to scale through here, again, 2 times matrix B, which again is negative 3, 9, 4, negative 1, 8, negative 6. And then I'm going to add 5C, which again is 0, 2, 3, 4, negative 2, negative 5. Before doing the work, we need to ask ourselves, can it be done? Even after I scale through, 2B is still going to be a 3 by 2 matrix. 5C is still going to be a 3 by 2 matrix. And we know that in order to add matrices, we have to have the same order. So yes, this one should work. We should be able to figure this out. So 2B, once I scale through, is going to be negative 6, 18, 8, negative 2, 16, negative 12. Again, this is 2B, and I'm going to try to add that to 5C, which scaling the 5 through is going to be 0, 10, 15, 20, let's see, negative 10, negative 25. Trying to fit all of this in one little slide here is probably going to be a bad choice. But again, trying to make this work. Again, adding these together now for the final sum. Again, we know that we can do this. We know that this is going to be possible, and more so that our final solution is going to be another 3 by 2 matrix. But again, adding row 1, column 1, row and column 1, and so on, we're going to get negative 6, 28, 23, 18, 6, negative 37, again, for that final solution. Number 3, we're asked to multiply A times C. So A is a 3 by 3 matrix. C is a 3 by 2 matrix. So the first question that we have to ask ourselves is, can it be done? And the answer is yes, it absolutely can be done, because the number of rows in the first is equal to the number of columns of the first is equal to the number of rows of the second. The way we always talk about writing it this way is that the middles match. In addition to that, we also know now, looking at your outside values, we know that not only will this work, but we also know that we're going to get a product of order 3 by 2. So knowing that we're going to get a 3 by 2, the way I would always encourage you to work through this is to build that. We're going to get 3 rows, 2 columns. And remembering that we're multiplying A times C, row 1, column 1 says that I'm going to multiply row 1 times column 1. So multiplying row 1 times column 1, 1 times 0, 0, 2 times 3, 6, negative 3 times negative 2, also 6. Moving over now, row 1, column 2. So row 1, column 2, again, first, second, third elements. Again, 1 times 2 is 2. 2 times 4, 8. Negative 3 times negative 5, positive 15. Moving down to row 2. So now we're looking at row 2, column 1. So row 2 times column 1. Remember the target. We just say it out loud. That tells us exactly what we're going with. Let's see, that's going to give us 0, 9, negative 8. Row 2, column 2. Over here, row 2, column 2. Do this where we can actually see the values that we're multiplying. So row 2, column 2, it's going to be, let's see, 10 plus 12 minus 20. Row 3, column 1, row 3 times column 1. This time that's going to give me, let's see, 0 plus 3 plus 8. Row 3, column 2. 3, column 2. Getting closer now, it's going to be negative 12 plus 4 plus 20. And now piecing this all together, hopefully you're all right with me erasing the work here for number 2, in fact all of number 2. But this is going to come together for our final answer. Again, we know that we're trying to obtain a 3 by 2 matrix, but that's going to give me 12, 25, 1, 2, 11, 12, again, for the final product A times C. So to finish this thing up, last one that we're supposed to look at is 3A plus 5B. Now we could jump right in and start scaling through and figure out 3A and 5B. And we could do that, but I know that when we figure out 3A, not actually solving it, but I know that that's going to be a 3 by 3 matrix. 5B, I know that after I scale a 5, that's still going to be a 3 by 2 matrix. So since these do not have the same order, we would have to say that that sum does not exist. Again, this is not possible. All right, so remember, in order to add matrices, you have to have the exact same order. In order to multiply matrices, the number of columns of the first must equal the number of rows of the second. All right, so last problem we want to take a look at. This is the write the system of linear equations as a matrix, AX equals B. So this is going right along the lines of what we did in class today. So if we wanted to write this out as matrix A, again, the coefficient matrix of 2, negative 5, 3, negative 8, times my variable matrix in this case appears to be x1, x2. And that's equal to the constant matrix of B1. All right, so that was what we were supposed to do in the first part A. Second part B, this is where we want to get into the idea that, hey, X is going to be equal to A inverse times B. So the real issue that we have in front of us, again, this was A, X, B, is we have to look at matrix A and figure out a way to find A inverse. So that's 2, negative 5, 3, negative 8. We need to find A inverse, which we know, again, if we use the formula, which we don't have to use the formula, but again, formula would be 1 over AD minus BC times my new matrix where D and A swapped places, B became its opposite, C became its opposite. So if we can jump in and pick up from there, again, we'll be able to, hopefully I'm not oversimplifying it, but fairly easily solve for matrix X, again, my variable matrix, by calculating and finding A inverse. Once we know A inverse, then it's a fairly simple multiplication with B. But I'm about to time out on this podcast, so I'm going to stop this one, pick up another one.